This lesson is part 2 of section 9.4. We're going to continue to solve trig equations, but specifically we'll be looking at trig equations that involve multiples of an angle. So we will be continuing to factor or use identities in order to solve trig equations. So we'll just see a little bit more examples now. Alright, so let's begin by solving equations where you have multiples of an angle. Now what I mean by that is if you look here, instead of seeing the sine of x, we see the sine of 2x. And here, instead of tangent of just x, we see the sine of, or the tangent of 3x. Now don't get confused by this. You don't need to, use an identity to rewrite this trig function at all. You can actually just solve this like normal. So if I want to solve and isolate here the sine of 2x, I would divide out that 2, and I'm left with the sine of 2x equaling root 3 over 2. Now we're going to first find all real solutions to this equation, and then we'll restrict our solutions to those that only fall within the interval 0 to 2 pi. So we'll do that in just a second. But when you're solving this equation here, think of this as just theta. So let's let theta equal 2x. You don't have to write this in or anything like that, but if we make that substitution, then really all I'm doing is solving this equation, which is similar to what we worked on yesterday. So if I want to solve for, here, then theta would equal, since this is the high point, right, on your unit circle, this is going to be that pi over 3 family. Oh, it's a terrible circle. So here at pi over 3 and at 2 pi over 3, that's where we have the sine of theta equaling to root 3 over 2. So those would be my two solutions, 2 pi over 3 and pi over 3. And if I were to do this with all real solutions, then that would be plus 2 pi n, since the sine function has a period of 2 pi. Okay, so that would represent all the solutions, but that's involving theta. Now, theta is equal to 2x, right? So if I want to get values for x, then that means all I'm going to have to do here is actually divide by 2. So I'm going to divide by 2. Let's divide this expression here by 2 first. So we have x equals pi over 3 plus pi n. So I'm just dividing both parts here by pi, or I'm sorry, by 2. Do the same thing here, and I get pi over 6 plus pi n. Okay, so that would represent all real solutions here. Alright, so we've answered part A. This gives us all real solutions. Now for part B, we want to restrict those solutions that fall between 0 and 2 pi. So let's start here with pi over 6. Now pi over 6 definitely falls between 0 and 2 pi. So if I want to write a solution set here, I'm just going to write it in set notation. Let's add multiples of pi now to that. So if n is equal to 1, then I have pi over 6 plus 6 pi over 6, which leaves me with 7/6 pi. Now if I want to add another multiple of that, so plus 2 pi, clearly you can see that 2 pi plus pi over 6 will not fall within the interval 0 to 2 pi, right? It's over 2 pi. So we can't continue to add multiples of pi over 6. So let's go to pi over 3. Now pi over 3 definitely falls in that interval as well. And if we add more multiples of pi, so let's try pi over 3 plus 3/3 pi, we end up with 4/3 pi, which is still within that interval. Now when we try to add another multiple of pi here, so 2 pi, again you're going to see that that's clearly outside your 2 pi interval. So here are the solutions. So you have 4 solutions now, as opposed to just the 2 that we would get if we were just solving the equation, the sine of x equaling root 3 over 2. Okay, so that would give us 2 solutions in the interval 0 to 2 pi, but this sine of 2x equaling root 3 over 2 gives us 4 unique solutions that fall within our interval. Okay, next up in problem 2, we're going to treat this equation as if it were the tangent of theta equaling root 3. So we have a positive ratio here of root 3 over 1, which means that we're looking at the coordinate 1/2 root 3 over 2, or negative 1/2 negative root 3 over 2. So that really only happens in the first and third quadrant, where your tangent will be positive, right? So the first quadrant and in the third quadrant is where the tangent will always be positive. Okay, so we're definitely looking at pi over 3, right? That's where you have the coordinate 1/2 comma negative, positive root 3 over 2. And for negative 1/2 negative root 3 over 2, that's going to fall in the third quadrant, and that would be 4/3 pi. So we have it, in order to answer part A, we know that theta is equal to pi over 3 plus, now this, instead of being 2 pi n, because the tangent function has a period of pi, I'm just going to do pi n here. And we have the other solution here, 4/3 pi plus pi n. Now as soon as we add a multiple of pi here, we end up with that solution here. So this actually encompasses all of the solutions that you would get from this. So I'm actually going to get rid of that. It's just, it's redundant. Now this is solving for theta though, and I want to know what the value of x is. So I'm going to set 3x now equal to pi over 3 plus pi n, and I'll solve for x by dividing by 3. So I have pi over n plus pi over 3n. So this represents my answer for part A, all real solutions. Now in part B, I want to restrict those solutions to the only ones that fall between 0 and 2 pi. So obviously pi over n for sure falls between 0 and 2 pi. And then after that I'm just going to add multiples of pi over 3. So I let n equal 1. So I have pi over n plus pi over 3. Find a common denominator here. And you have 4/9 pi. So now we're going to add another multiple of pi over 3. So let's let n equal 2. So we have 2/3 pi. Right, that's 2/3 pi. Common denominator again. And we end up with 7/9 pi. So we just keep adding multiples of this pi over 3. So let's do 4/3 pi now. Common denominator again. We end up with 13/9 pi, which also still falls between 0 and 2 pi. Then when I add the next multiple, so 5/3 pi plus pi over n, I have 15/9 pi plus pi over 9, so that's 16/9 pi. And then when I add my next multiple, that next multiple would be 6 pi over 3, which is 2 pi. So you have 2 pi plus pi over 9. Clearly that will not fall within your range here, or the domain you're searching for, that interval. So these are the only solutions between 0 and 2 pi. Okay, in our next problem here, some of you might be tempted to try to use a trig identity here to manipulate the cosine of x over 2. I actually wouldn't do that here in this case because you can actually add this cosine of x over 2 to the other side so that you now have 2 cosine x over 2 equaling root 2. Now to isolate this cosine of x over 2, I would just divide by 2. So I'm looking at this equation here, which I can think equivalently to the cosine of theta equaling root 2 over 2. So the cosine of theta is equal to root 2 over 2 in the fourth quadrant, right? So you've got your pi over 4 here at root 2 over 2 comma root 2 over 2. So the cosine here is going to be root 2 over 2. Now it's also going to be positive root 2 over 2 in the fourth quadrant here at 7/4 pi. So we have theta equaling, to answer part A here, well, kind of partially answering part A, it'll be pi over 4 plus 2 pi n, and 7/4 pi plus 2 pi n. Alright, so that's where we have theta though. I want to know what x is equal to, so again I make that substitution here. That's x over 2, and I'm going to solve for x. So I'd have to multiply by 2 here, so I end up with x equaling pi over 2 plus 4 pi n. And again, multiply by 2 here, you end up with 7/2 pi plus 4 pi n. So this represents all solutions that would satisfy this original equation. Okay, let's answer part B now. We're going to look for solutions that lie between 0 and 2 pi. Alright, so pi over 2 definitely falls between 0 and 2 pi, but as soon as I try to add a multiple of 4 pi to that, so if n is equal to 1, clearly this is going to fall because the 4 pi, I'm adding 4 pi to this, it does not fall within that interval. So that's the only solution I can get here. Now 7/2 pi is already itself outside of that interval, so this is actually my only solution in the interval 0 to 2 pi. Alright, the last problem in this section actually looks like it doesn't belong here because we don't see a multiple of an angle right away. We just see the cosine of x and the sine of x. But I'm going to rewrite this as 2 times 2 cosine x sine x. And then from here, I recognize that this, I can use a double angle identity and rewrite that as 2 times sine of 2x. And from here, to solve, I just divide out that 2. So I have sine of 2x equaling root 3 over 2. And now this is just like question number 1. So I'll let you guys try to work on that one and see if you guys get the same solutions as we did for problem 1. Okay, in this section here, we're going to transform our beginning equation so that we just end up with one trig function as opposed to the multiple trig functions that we originally see. So in number 5, I'm actually going to break a rule that I talked about yesterday, which was you don't want to divide out a trig function. Now in this case, we can. Okay, in the problem that I showed you, by dividing out, I think it was the tangent of theta or something, by dividing that out we ended up losing solutions to the original equation. But in this case, if we divide out the sine of alpha, we end up not losing any solutions from this. So we're going to assume, for one, that the sine of alpha does not equal 0. Because even if it were to equal 0, we don't end up with any solutions from this. So for example here, that would be values of pi, 0, pi, 2 pi, and so on. If you plug those values into your original equation here, you have 0 times root 3 equaling either positive or negative 1, depending on which of these you're plugging in. So clearly that's not true, so we don't lose any solutions from sine of alpha equaling 0. But we're going to assume that it does not equal 0. Okay, so we don't lose that function here. So we end up with the square root of 3, oops, shouldn't have gotten rid of that. That cancels here and leaves me with the cotangent of alpha. So now I have one trig function as opposed to the 2 that I originally had. Okay, so now let's look at trying to solve this. Now, if you're using a full unit circle here, you have two quadrants where the cotangent is going to be positive, and that's in the first and the third quadrant. So we're looking for a ratio of x over y to equal root 3. Now that happens when x is root 3 over 2 and when y is 1/2, or when they are negative, right? Oops, I shouldn't say positive or negative since it's very explicitly either negative root 3 over 2 and negative 1/2 or positive root 3 over 2 and positive 1/2. So those values here in our unit circle would be at this pi over 6 here and over here at 7 pi over 6. Okay, so the reason why I was saying that the cotangent function is periodic, right, and its period is pi, we actually end up not needing this at all, because when I write all of the solutions, pi over 6 plus pi n, since it's multiples of pi, that includes 7 pi over 6. Okay, so again, it's redundant. I don't need to actually include that one, so this shows all solutions to this equation. Oops, sorry, I should write in alpha equals. Okay, now for part B, let's find all of the solutions that work from the interval 0 to 2 pi, and this time you can include 7/6 pi. So this would be the solutions on 0 to 2 pi. Okay, next up in number 6, I see that I have two different trig functions here. Now, I can rewrite the secant squared x here using a Pythagorean identity, and I can substitute 1 plus tan squared x in. So now I've just transformed that, so I just see one trig function here. I also recognize that this is now a quadratic-like equation, so if I subtract that 4 over, I have this equation which will factor into the tangent of x minus 3 and the tangent of x plus 1. So now I'm going to look and solve two different equations, the tangent of x equals 3 and the tangent of x equals negative 1. Now when we were solving something like the sine of x or even the cosine of x equals 3, we would stop there and write no solution from here because the range of our sine and cosine functions is between negative 1 and 1. But that's not the case for our tangent function. Remember, if you graph your tangent function, we have an asymptote at pi over 2 and an asymptote at 3/2 pi. But we have this general shape here. So you can see that its range is definitely all reals, right? It hugs those asymptotes and goes to positive and negative infinity. So there, it also has a period of pi, so this is going to be repeated over and over again. And we definitely have multiple values for which x, the tangent of x, I should say, should equal 3. So it's definitely possible here, 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 it could equal 3. So if we were solving this, or when we are solving this for all reals, your exact answer here needs to involve inverse tangent. Okay, so I take the inverse tangent on both sides and I end up with x equaling the inverse tangent of 3 plus all values of pi n, multiples of pi n. So that would give me the exact values. Now we're going to use our calculator too to find those to answer part B, okay, on an interval of 0 to 2 pi, but we're going to hold off on that in just a second. Let's do the tangent of x equals negative 1 because that's a little bit easier for us. The tangent of x is negative in the second quadrant and in the fourth quadrant, okay, and that occurs at negative root 2 over 2, root 2 over 2, and positive root 2 over 2, negative root 2 over 2. So that's 3/4 pi, right, and 7/4 pi. So when we are answering part A here, whoops, I don't even need to write that again because it's right here. So to answer part A, when you do 3/4 pi plus pi n, that's including 7/4 pi. So you actually don't need that because it would be a little bit redundant here to include that, but it definitely needs to go with both of these here. So here are our solutions, all solutions. And then when we do part B, we would include 3/4 pi and 7/4 pi. Okay, but then for this part, okay, this is a little bit more work for us. Okay, so let's take out our calculator. Okay, let's make sure our mode is in degrees, or I'm sorry, radians. So it's definitely in radians here, and let's go back and let's type in inverse tangent of 3. Alright, so I get positive 1.249, so that's good. Let's say I was trying to do the inverse tangent of negative 1. Okay, that value here is negative, and that would not fall within our range of 0 to 2 pi. So, you know, you got to be careful about that. Make sure you're adding multiples of pi back to it. So if I do that, I should end up with that first value here, 2.356. That's going to be that 3/4 pi right there. So if I just did 3/4 pi, I get 2.356. So you can always verify too using a calculator, but I just wanted to show you what you end up with. You know, if you have a negative value, make sure you add back the multiples of pi to get it within the 0 to 2 pi range. Anyhow, sorry, let's go back to the inverse tangent of 3 here. Okay, so there's one solution here. So I'm going to write that down as being part of my 0 to 2 pi range. Okay, so oops, from 0 to 2 pi, so far I have solutions 1.249 radians. Okay. And let's find another one. We're going to add another multiple of pi here, so I'm just going to add pi to that. Oops. Oh my gosh. Thank you for your patience. Sorry. Delete. There we go. Okay, so I have another one at 4.39, and that's still less than 2 pi. So another approximate value there. But as soon as I try to add another multiple of pi to that, so that would be like taking 2 pi, you know, let's see, 1.24, let's just do that in here for you. Inverse tangent of 3 plus 2 pi. Clearly, this would be outside of the range of 2 pi, but I just want to show you 2 pi, that value is roughly 6.28, so clearly over that range. So these would represent the solutions then, from 0 to 2 pi. Okay, so I'd like you to try 7 and 8 now on your own and check with the key. Obviously, no two trig equations are exactly the same, so you want to make sure you're getting enough practice so that you're using all the strategies that are available to you. So go ahead and try 7 and 8, and then check with the key. Okay, in the last problem here, we're going to be using a calculator. We're going to solve the equation, the cosine of the sine of x equaling the cosine of x. So be careful, this is not saying the cosine of x times the sine of x. Sine of x is actually the input for cosine of x, so make sure you don't confuse that with this. Alright, now when you graph this, you're going to treat basically each of these as its own curve. So we're going to have y equals the cosine of the sine of x, and y equals the cosine of x, and we'll see where these two curves intersect. So I have already typed that into my calculator, so just type in cosine of sine of x and cosine of x. I'm using a different calculator because I want you to see the colors here. When I go to graph this, you might not need to adjust your window, so just hit zoom 6 before you even graph this, because you might not even be able to see the picture of it, since your window might be adjusted to something crazy. Anyhow, so here's the graph. So clearly I'm seeing multiple intersection points, right? There should be an infinite number of solutions to this, but we're only interested in the ones that are from 0 to 2 pi. So I want to get a better picture of this. Now, in my window, I can adjust the x min and x max to 0 and 2 pi so that I'm restricting it to only those values. So I would just be careful though, you know, if your solutions are at 0 and at 2 pi, then you might not be able to calculate them because your calculator needs to be able to see that domain. And if you type in 2 pi, it's going to truncate some values so it doesn't get the full 2 pi in there. I hope that makes sense. But anyhow, so I'm going to do 2 pi plus 0.1. And see how it already just calculated it for me. And for my y min and y max, I'm going to adjust this to, let's say, -2 to 2, because I know it doesn't go beyond -1 and 1. The cosine and sine functions, their range is between -1 and 1. Okay, so anyhow, when I go to graph this, now I should get a much more zoomed in picture. Okay, so this is going to take forever. Let me pause. Okay, so here's the graph. Now, I already know what the solutions are. They're actually 0 and 2 pi. So that's why I adjusted our window slightly, so that when I hit second calc and I try to find the intersection here, it'll let us find the intersection. And it'll ask first curve and second curve. Just hit enter, enter, enter. And when it asks guess, same thing. So the intersection here is 6.28, which is 2 pi. And to find the other intersection, I would just hit second calc, intersect again. And I'm going to scroll over. This is going to take so long. So I'm not going to even bother doing this, but I would scroll over closer to this coordinate here, where the other intersection is at 0. So I graphed it somewhere else so that you can see it a little bit better. So clearly, we have multiple solutions here, but from 0 to 2 pi, we get one at 0 and one here at 2 pi. So those are our two solutions to this particular equation. Okay, so our solution set on this particular interval is 0 and 2 pi. Now be careful, if that had not been inclusive like this, then we would not have any solution at all. But anyhow, you can always double check this algebraically too. Let's say we input this back into our original equation here. So we have the sine of 0, okay, and the sine of 0 is 0. So I'm taking the cosine of 0. And on the other side, I have the cosine of 0. Obviously, these are equal. They're both 1. And then if I type in or plug in the sine of 2 pi, okay, so I have sine of 2 pi is 0, and the cosine of 0 is 1, and the cosine of 2 pi is also 1. So that also works, okay? Alright, so basically the reason why I wanted you to do this problem on your calculator is just so that you see how you can adjust your window so that you're restricting, and it just basically helps you out. When you go to graph something and you want to just restrict from 0 to 2 pi, you can see that you found all of the correct solutions. So it's just a helpful tool, okay? Alright, nice job. I'll see you guys in class tomorrow.